Welcome to this video in which I provide an introduction to confirmatory factor analysis. My name is Geiser. I'm an instructor and statistical consultant with QuantFish, and on this channel I present weekly statistics tutorials. On Tuesdays I usually talk about an analysis in the Mplus software, and on Thursdays I present more general issues in statistical analysis, including factor analysis, structural equation modeling, multi-level analysis, and latent class modeling. If this is something that interests you, then please subscribe to this channel. Also, don't forget to check out the description for additional resources, including a link to my free weekly statistics newsletter, as well as courses that I teach for QuantFish. In this video, I will provide an introduction to confirmatory factor analysis that is mostly non-technical and conceptual in nature. So what is confirmatory factor analysis good for, or what is the motivation for using confirmatory factor analysis? One of the main motivations is that when we use measurements in the social sciences, for example questionnaire or test data, then such data typically is contaminated to a certain extent by measurement error. So meaning many of the measurements that we take, many of the items or test scores contain random measurement error. And the problem with random measurement error is that can cause bias when we estimate correlations between variables, or when we use multiple regression analysis to examine relationships between variables. Then measurement error, or unreliability as we say, can lead to an underestimation of correlations and regression coefficients, and can lead to incorrect inference, meaning incorrect tests of significance, and so the results then may be biased and misleading. When you have unreliable measurements and you look at correlations between these measurements to find out about relationships between variables, then those may not be accurate. And that problem is exacerbated when you look at more complex multivariate models such as path analysis, where we may have mediator variables and complex paths between a chain of variables. And so then when the relationships become more complicated, then those path coefficients and effects may either be over or underestimated, and the direction of the bias can be difficult or impossible to predict. And so therefore we want to correct for measurement error, and confirmatory factor analysis provides us with a tool for measuring the amount of error variance in our observed variables, so quantifying unreliability and then separating the unreliable portion of variance from the reliable portion of variance, the factor or latent variance, so that we can then work with latent factors or true score variables that are corrected for measurement error. So this is one of the important goals of confirmatory factor analysis, is to separate true score variance, true inter-individual differences, from variability in the scores that is simply due to random noise. And so we do that by introducing latent variables or factors in measurement models in confirmatory factor analysis. So confirmatory factor analysis connects observed and latent variables in so-called measurement models, and that way we can account for measurement error and separate measurement error from true score variance, and we can estimate the reliabilities of the observed variables as part of the analysis, so we can determine what proportion of the variance in our measurements is reliable variance. Let's take a look at a simple factor model with just one factor. And so one conceptual model that we could imagine could be one where we want to measure physical health, and we want to measure true physical health, meaning individuals' true scores or latent scores. And so then with observed measurements we can try to get at that factor by using more than one indicator. So one indicator, for example, of physical health could be the number of sick days in a given year. Another indicator may be the number of physician visits in a given year. So we can imagine that people who report more sick days have on average lower physical health. People who go to the doctor more often have lower physical health. So those two measurements could serve as indicators of a latent factor that we may call physical health. And obviously, the measurements are not perfectly reliable. So a person, for example, may not perfectly recall the number of days that they were sick in a given year. Also, there may not be a perfect record of the number of physician visits. Even if we had a perfect record of how many days or how many times a person went to the doctor, then some of those doctor visits may not be related to sickness. Perhaps some of them were only for routine blood draw, for just checking the wellness of a person, but not actual sickness. And so there will be some measurement error involved in those counts of sick days or physician visits. And so therefore, only part of the variance in these indicators, part of the inter-individual differences in these indicators will reflect true differences between individuals in their physical health. Another portion of individual differences on those measurements will be due to random error. Now, we can still assume that those two measurements will be correlated, positively correlated, because people who are less physically healthy will tend to report more sick days and they'll tend to report more physician visits. There will be a positive association. However, that correlation will probably not be perfect due to there being measurement error in either one of the scores, which lowers the correlation between the two, even if they were perfect, in theory, perfect indicators of physical health. There will be measurement error, and therefore the correlation between the two measurements will not be perfect, but there will be some correlation, and probably a substantial correlation, because those are strongly related indicators. And so the idea in factor analysis is that the factor, the latent variable, accounts for that covariance or correlation between those measurements and basically sucks it up. So the variance of the factor is identified in part by the covariance between those two measurements. So naturally, so to say, the variance parameter, the factor or true score variance parameter, is a function of the covariance. And so that, so to say, covariance is indicative of reliable variance because it is replicable, so to say, across two different measurements. So that's the idea behind this, is that the correlation between the two indicators is due to the fact that they are measuring the same common factor, and so that's therefore reliable variance. In addition, there's error variance that is unique to each indicator, that reflects random error, and also potentially specific variance in each indicator that's not shared with the other indicator, and that's here reflected in the epsilon 1 and epsilon 2 error variables. So that's what a simple one-factor model could look like. You can have more indicators, more than two, and it's typically recommended for identification and stability of the model to have at least 3 indicators per factor. However, 2 indicators is typically the minimum that can work with certain constraints. Now let's take a look at this model in more formal terms. So more formally, we could say we have a latent variable of factor f1, and that factor is measured by 2 indicators, y11 and y21. The first index here refers to the variable or item. The second index refers to the factor. So this is the first indicator of f1, and then this would be the second indicator of the same factor. We have factor loadings, lambda 11 and lambda 21, that measure the strength of association between each variable and the factor, and we'll see later that the loadings are related to the reliabilities of the indicators. In particular, the standardized factor loadings are directly linked to what we call reliability or communality in factor analysis. Furthermore, we've already seen that there are also error variables for each indicator, epsilon 11 and epsilon 21. These error variables are uncorrelated with the factor F1, so they represent unique sources of variance that are not accounted for by F1, and that's to say one of the points of factor analysis is to have a variance decomposition into reliable or true score variance on the side of the factor F1 and unreliable or error variance on the side of the error terms epsilon. So these are by definition uncorrelated with the factor F1. They may be correlated with other error variables. In this model it wouldn't make sense because here the common variance between y11 and y21 is already accounted for by the single factor, so it definitely wouldn't make any sense to allow a correlation here between epsilon 1 and epsilon 2. However, when you have more indicators and or more factors, sometimes some of the indicators share specific variance with other indicators, and then some of those error correlations may be meaningful and are sometimes estimated. This model can be described by formal measurement equations. For the first variable y11, the equation looks like this. y11 is the dependent variable here on the left-hand side, and so y11 has an intercept in the equation alpha 11, so that is statistically or mathematically that's the same thing as a constant intercept in a linear regression model with a single predictor. So we have this additive constant or intercept, we have a multiplicative constant that we call factor loading, and that's a linear regression slope parameter lambda 11. So that is to say that links the variable to the factor, and then we also have an error term in the equation. So you could think of this measurement equation as being a linear regression equation with a single predictor that is a latent or unobserved variable. And we have the same equation also for y21 with a separate intercept, with a separate factor loading and a separate error term. Alpha and lambda are constants, they are parameters that are estimated, or at least some of them are estimated in a factor model, whereas f and epsilon are variables for which we have variances as parameters in the model. In summary, in this model we would have as free parameters the two intercepts, the factor loadings, the error variances, and the factor variance. And in some models we would also consider factor means, for example when we look at longitudinal data and we want to examine mean changes in factors across time, or in multi-group analysis when we want to look at different group means and test whether they are different. Now, not all of these parameters can be formally identified, particularly when you have a small model like this, and I'm not going into the details here, but on the QuantFish channel you can find other videos that deal with factor models with one factor and two indicators, where I discuss identification in detail and show under which conditions a small model like this can be identified. Now, part of the confirmatory factor analysis is, or what is often of interest, is to determine the reliabilities of the observed variables as measures of the factor. We want to know how precise the measurements are, how much measurement error there is in the scores, and I told you that the error variance parameter is one parameter that is estimated that quantifies unreliability, and then there's also the factor variance that quantifies true score variance. And so to standardize the reliable variance, we can define a reliability coefficient that is given as lambda squared times the variance of f1 divided by the total model implied variance of y11, where the total variance here in the denominator is given as lambda squared times variance f plus variance epsilon, and all these parameters are estimated, the factor loading, the factor variance, and the error variance, and so therefore we have a complete variance decomposition in this model because epsilon and f are not correlated, so those are additive components of variance here that go into the denominator of this reliability formula. Now, when you have a standardized solution, which we can also estimate in confirmatory factor analysis, then the factor variance would be 1.0, and also the denominator variance of the observed variable, variance y11, would also be 1, and then all that remains is just simply lambda squared when you have standardized variables. And so therefore the standardized factor loadings squared are equal to reliabilities in a simple structure model like this one. That's why people often look at standardized factor loadings, because they're directly related to the reliabilities. Now, what does the reliability coefficient tell you? It tells you the proportion of variance in a measured variable that is true score variance or factor variance. So, for example, if the reliability coefficient were 0.8, this would mean that 80% of the variance in y11 is true score variance, and only 20% of the variance is error variance. The standardized factor loadings in their unsquared form are equal to correlations between the variable and the factor, as long as each variable loads only onto one factor. And so that's why the standardized factor loadings are easy to interpret, because they directly measure the strength of association between a variable and the factor, and then the standardized loadings squared give you reliability in the standardized solution. We have the same definition for the second variable, so the reliability of y21 would be the second loading squared times the variance of f1 divided by the model implied total variance of the observed variables. So this allows you to determine measurement precision through CFA. The psychometric property of reliability can be determined with such a model, and that can often be useful if you want to find out about the quality of your measurements. Now, typically we estimate models that contain more than one latent factor, and often the purpose is actually to look at correlations between multiple factors and estimate latent correlations that are corrected for measurement error. I told you initially that one of the motivations for confirmatory factor analysis is that observed scores are contaminated by measurement error, and therefore correlations between observed scores may be biased, may be attenuated or underestimated. And so when we use confirmatory factor analysis with multiple constructs, multiple factors, then we can look at latent correlations that are corrected for measurement error. So here's an example of a two-factor model. So in addition to our physical health factor, we may also have another factor that's called subjective health. So we might be interested in looking at whether physical health as measured by more objective parameters is related to how a person subjectively judges their health. So we might have a factor for both. And then we can also look at the correlation between those two factors. In the unstandardized CFA solution, that would give us the covariance. In the standardized solution, where the factors have unit variances, this would give us the correlation along with the standard error and a p-value, a test statistic, so we can test the significance, the statistical significance of the correlation and look at its magnitude. And so that's one other major benefit of CFA, is that it allows us to estimate latent correlations that are corrected for measurement error. In summary, what are the goals, or what are important goals of confirmatory factor analysis? One goal that I have not yet discussed in detail is that we also obtain tests of model fit, and so one goal is to test the hypothesized factor structure against the observed data. So we can test whether a theoretical model is in line with our data. We obtain a chi-square test of model fit for over-identified CFA models, and so that allows us to reject incorrect models, figure out what whether scores are unidimensional or multidimensional, for example, and so that can be tested, and we can also compare different models statistically using fit statistics that are provided as part of the estimation of a confirmatory factor analysis model. Furthermore, we saw that we can estimate the indicator reliabilities to find out about measurement precision and the amount of measurement error in our observed variables. So then we can say something about the measurement quality of those indicators. Also, we can see whether the indicators measure on more than one factor. So are they unidimensional, or do they maybe have cross loadings on other factors? That can all be determined based on tests of model fit and evaluating how the model aligns with the data. And then we saw that we can, in multi-factor models, look at latent correlations between multiple factors that are then corrected for measurement error, so we get a better picture for the strength of association of different attributes when we look at those correlations between latent factors, as opposed to looking between correlations of observed variables that do contain error. In more complex models, we can also look at more complex variance decompositions. For example, when you have longitudinal data and you want to separate trait and state components of the true score variance, you can use latent state trait confirmatory factor analysis models, where we may have, for example, first order factors that represent the persons in situations, and we have a higher order trait factor that captures stable variance across time, and then first order residual factors that characterize state residual effects. If you're more interested in those types of models, I also discuss latent state trait models in videos here on this channel, and bifactor models, which serve also the purpose of decomposing the variance into different components, general factor and specific factor components. And so those are special types of confirmatory factor analysis models. Also, when we have multiple rater data or multi-trait, multi-method data, where we collect data from different methods or different raters or sources, then we can separate the variance that is shared between raters from the variance that may be unique to each rater versus measurement error. And then finally, another goal of factor models can be to analyze longitudinal data. When you have repeated measures, then confirmatory factor analysis is also a very powerful tool for looking at change across time, because it allows us to look at latent change, meaning change in the true scores. We can define latent difference score variables or latent change score variables using latent growth curve models or latent change score models, for which I also have videos here on this channel that you can check out. And there's a particular benefit to using CFA for longitudinal data, because observed difference score variables tend to be particularly unreliable, because when you take the difference between two observed variables, then the unreliability or measurement error variance from both time points enters into the difference score, and so then the difference score may contain a lot of unreliable variance. And so then if you're interested in studying inter-individual differences in change over time, and you want to know why some people changed more than others, then that might be problematic when you have a lot of error variance in your difference scores. And so with latent variable difference score models, we can look at latent change scores that are corrected for measurement error. Also, there are other types of longitudinal CFA models that allow us to study causal effects, for example, autoregressive cross-legged models and many related types of specific models. So it's a very flexible tool to handle many types of data. Also, for example, multi-group comparisons can be conducted with factor analysis, and we can test for measurement invariance across groups in cross-cultural comparisons, for example, to make sure that our measurements function in the same way in different cultures. So that's more powerful than, for example, analysis of variance, where we would simply assume that the groups are comparable. With CFA, we can actually test that, and then we can test for latent mean differences, latent variance differences, and latent covariance differences across those groups. I also have some videos on multi-group analysis here on this channel if you're interested. Also, if you're more interested in confirmatory factor analysis, on QuantFish, go quantfish.com, I offer a variety of workshops on using factor models with Mplus. For example, I have a whole course on factor analysis, exploratory and confirmatory factor analysis, where I discuss both basic and more specialized confirmatory and exploratory factor analysis models. I offer a course on structural equation modeling with Mplus, longitudinal CFA and longitudinal structural equation modeling, and other types of models that I discuss there in those courses, so check those out in the description as well. I hope you liked this video. If you did, then please hit the like button, subscribe to this channel, and don't forget to check out the description for additional resources, and I'll see you next time.